you'll start to notice the pictures of the instruments we've been using and be able to depict them and know what they're used for. So that's part of the idea. So, and the disadvantage to using a cross staff was what? You were blind because you're looking at the sun, right? So that was a big problem, and it was a widely known one, and it was one of those occupational hazards that people just accepted for a long time as part of the, part of the deal you signed up for. But that was always bothersome to people. The astrolabe, the one good thing about that was you didn't have to look into the sun to use it because you could project that little dot. That was also true of the mariner's quadrant because, like the astrolabe, there's a couple of veins with 2 holes in them, and you project one dot onto the hole on the other vein, and that can give you a reading. But again, those were a problem because if the ship's moving around, those were gravity indexed, and the instrument itself is moving around. And in the case of the astrolabe, the instrument might be moving around. In the case of the quadrant, it's the plumb bob that might be moving around. We might use a quadrant next week. But so that was a problem. Whereas the cross staff was indexed to the horizon. And so you can fix one leg of the transom or one edge of it on the horizon and the other on the sun. And if you're careful and you make sure to try and blot the sun out with so you're doing the upper limb of the sun, you might preserve your eyes for a few more years before you go blind from doing that. In any case, solving that problem was an issue, and so along came this Elizabethan mariner. His last name was Davis, and he invented an instrument so ancient it actually predated his employment with the Maritime Museum of San Diego. That's how old it is. In any case, if you saw the movie or read the book Shogun, the main character in Shogun is modeled after John Davis, who had an adventurous life, found Davis Strait going up into the into the Antarctic, tried to find the Northwest Passage, was buddies with Drake and Cavendish and Hawkins and all those guys, and wound up being killed by Japanese pirates off Sumatra. So interesting in character. And along the way, he invented this instrument called a Davis backstaff or an English backstaff. So now we're going to decamp out to the aft deck and play with this one just like we did last time with a cross staff. Okay, everybody up for that? Okay, let's go do it. So the way this guy works is there's 3 different veins. This is the horizon vein here, okay? It's got a slot in it through which you look at the horizon. Now, of course, we don't have a horizon here, so we're just going to use something over there like the shear line of the Star of India. And then you've got these 2 sliding veins, okay, one of which has a little peephole in it, okay, and that peephole has a line that comes across on this side and lines up here, and that is, so I understand it, where you read the degrees off on this scale here. This other one is the shadow vein, and it casts its upper edge, casts a shadow across this slot when you're looking at the horizon. And you're staring away from the sun when you do it, okay? So if I look at this, and maybe if I get a couple, just get out of the way for a second, I'm going to look through this peephole. I'm going to try and line up the vein with the Star of India shear line, and then I'm going to mess with these 2 veins in tandem. GPSs, right? My guess is of the people that do celestial navigation that have used one of these or a cross staff, well, you guys have probably tripled the number of people on Earth until today that have done that. Because you don't even get to see these very often. Okay, very good. Any questions about the use of the instrument? Like I said, I still haven't figured out myself how to read the scale properly, but I'll put some time into it, maybe have a little bit of insight. So what we're going to do is we're going to start off here with the navigation part of today. And we are going to work out a regular sight and all the way through plotting it, because plotting is probably the thing people might have had. Some of you might have had the least experience with, particularly last time I couldn't get that gizmo to work. So we're going to plot it, and then after that we're going to go to the next subject, which will be noon sights, which we kind of closed with last time. So this particular day in question is August 11th, 2024. The DR position, which happens to be Bird Rock, just so you know, is north 32 degrees, 44 minutes. West.
Ray, is there any way you have that on the board? Or?
Yeah, I'll put it up. I'll get, but I'm just going to read it to you guys now. If you could jot it down, I will put it up there. My handwriting isn't always great, but west 117 degrees, 15.4 minutes. That's the DR position, okay? What was the question? Yes, absolutely. So the latitude was north 32 degrees, 44 minutes. Longitude west 117 degrees, 15.4 minutes. The local mean time, well, first of all, let's back up a little bit. The height of eye was 20 feet. Was the sun, lower limb. The local mean time of the site started off on the even minute at 15 hours and 4 minutes, to which we added by the stopwatch 5 minutes and 43 seconds. Okay. The HS was 54 degrees, 18.8 minutes. So I'm going to read you the LMT again. It was, first of all, height of eye, 20 feet. The local mean time was 15 hours and 4 minutes, to which you add the stopwatch time of 5 minutes and 43 seconds. And the HS is 54 degrees, 18.8 minutes, no index error. Okay, now I'm going to get a transparency and write this out, so hang on a second.
Gosh, you get to intercept 49?
Okay, we're going to go ahead and work this out, or try to. So some of you may not be quite done yet, but let's just follow along at this point. We'll get to the point where we plot it. So I didn't leave very much room for myself here to do this, but if I put in here time zone is +7, then we get 22 hours, 09 minutes, 43 seconds. So that is GMT, right? Everybody get that? Okay. All right. So now we've got the basic information down. We're going to correct the sextant. So if we have 20 feet of altitude above the surface of the water, what is our dip correction? It's minus something, isn't it? Okay, 4.3. So that gives 54 degrees, 14.5 minutes. And the main correction is what?
That's 15.3.
15.3? Everyone good with that? 15.3? Does that work?
Yeah.
Okay. And that is our HO. Okay? 54 degrees, 29.8 minutes. Okay? Okay, so next what we're going to do is we're going to get the GHA. So GHA for 22 hours on August 11th is what? 148 degrees, 44, is there a point something, or is that?
Point zero.
Point zero. Okay. And then for the, if we go to the gray pages, for the minutes and seconds for this leftover 9 minutes and 43 seconds, what do we have to add to that? 2 degrees, 26.3 minutes.
Oh, wait.
Oh, it's a different number.
No, yeah, I think if I get a different number, because I thought there was a 45 over there for the time, seconds. So if there's 43 seconds, that might have been the difference.
Oh, okay, so it's 25, so now we think it's 25.8, is that right? I'll just look at mine here and see if I got the same thing. Yeah, I got 25.8. So this is 25.8. Okay, so that's 0.8 minutes. What is that? 69.8 minutes, 150 degrees. You can't really have 69 minutes, so this gets to be 151 degrees, 09.8 minutes for a GHA. Okay? 151 degrees, 09.8 minutes. Are we good so far? Okay, let's write down, then let's over here, let's just go do declination. For the day and the hour, what's our declination? It's north something.
North.
14 degrees, 54.3. Okay, what what's our little D number? Minus 0.7, I think. So we combine 0.7 with this leftover 9 minutes and 43 seconds, and what does that give us? A minus what? 0.1? Everybody get 0.1 for the corrective factor? Okay, so 54.2, 14 degrees, and that is the declination, okay? Everyone with me so far? Yes. Okay. Yes. You want me to move this up some? How about that? Oh, okay.
Oh, there you go.
Bring the page down.
There we go.
Okay. Yeah, I'm sorry the field of view is not the greatest, but this is the last numbers we've written down. So we've got GHA, 151 degrees, 09.8 minutes. Declination is north, 14 degrees, 15.2 minutes. Okay, so now we pick an assumed longitude, then we subtract it from the GHA, ends up with a whole number, don't we? So our assumed longitude, since our DR position was 117 something, 15.4, the closest one would be 117 degrees, 09.8 minutes. So 151 minus 117 is what?
34.
34. Okay. 34 degrees, that is our LHA. Okay, and our assumed latitude, okay, is north 33 degrees, just kind of like it's going to be for this whole class. So, as long as we're using actual sites. So, assume longitude 34 degrees, assume longitude 117 degrees, 09.8, yields 34 degrees as an LHA, and the assumed latitude is north 33 degrees. So now, we go to the 249 pages, and we're going to find an HC on the cross-indexing LHA of 34, right, with declination 14. And what do we get for an HC? $53 degrees, 45 minutes? Oh, we've got some different numbers now. Okay, let's just out of curiosity, let's see what I got.
53:45.
Yeah, I've got 53:45. Okay, HC, 53 degrees, 45 minutes. We have another one of those little D's, right? And what is that?
36.
And is it decreasing or increasing? Each time we bump over another degree, higher declination? I think it is decreasing there. Oh, actually, no, I don't think it is. It's increasing. So it's plus 36. It was decreasing when it was the little d applied to declination, but applying to this, it's increasing. So when we cross-index 36 with this 54.2, well, let's just round that to 54. So 36 and 54 on table 5 gives us what? What's the addition we have there? Okay, 32. So I read when I did this, I read the number wrong, I think. I got 39 being a little b, but I just must have read tiny numbers. That's what happened. So 32. So this is 777. 53 degrees, 77 minutes. And let's look at our HO for a second. Okay, which is the same as 54 degrees, 17 minutes. Right, that's the HC. And the Z number that we pulled off, what is that?
13.
What is that?
113.
113. And if the LHA is less than 180, we're going to subtract that from 360, according to the formula up there, and that gives us what? 247 equals the Z in. That sounds about right, because that's off to the southwest, right? Okay.
So your HC there, your 53 degrees, 77 minutes, wouldn't that go to 54 degrees, 17 minutes?
Right, which is
Oh.
what I have right here.
Oh, okay. Oh, I didn't see that. It got cut off. Okay.
Okay, I need to move this up a bit, probably. Okay, so we've got an HO of 54 degrees, 29.8 minutes. We've got an HC of 54 degrees, 17 minutes. And so when we subtract that, that's 12.8. And the HO is bigger, so that's towards, right?
Yeah.
Okay. Okay. All right. So now, everybody with me so far? Question?
Can you push that? We can't see.
Oh, sorry. Let me push this up a bit. Does that help? Is that better?
A little more, yeah.
A little higher? Okay. Everybody read that?
Yeah.
Okay. Okay, so once again, we're going to start plotting from a position of assume latitude of 33 degrees north, assume longitude of 117 degrees, 9.8 minutes west. We're going to draw a line on a course or a bearing of 247 degrees true. We're going to go out 12.8 miles on that and draw a perpendicular. So as everybody has this, I'm going to shift over to another device.
Yeah.
Okay. So let's get off for a second. Okay. Okay, so our assumed latitude is 33 degrees north, which is right here, right? 33 degrees north. Our assumed longitude is 117. What? Did someone give me the assumed longitude? 15.4. Okay, so that's 15.5.
No, it'd be 9.8.
Oh, was it 9.8?
Yeah, the assumed is 9.8.
Okay, 9.8 is right there. So our assumed longitude is right there. Okay? Alrighty. Our assumed our ZN is what?
247.
Okay. I think that's about 247 there. And of course I've already drawn this line, so that helps. And then we come out, how far? What's our intercept?
12.8.
12.8, okay. And I measure this, so let's measure that to 13. Okay, and my initial one, I'd written down the numbers wrong, so sorry about that. So this one isn't as close as I thought it was going to be, but when we draw this out, that's our line of position, and this was our DR position. So this shot is actually, it's about 2 miles off. Okay, now what would be a source of error for this? And in me looking at and remembering what it was like on the 11th, it was pretty foggy on the horizon, so I might not get an actual horizon. So So it could have been 3 hours there. Also, I think I might have underestimated the height of I because I was standing on the cliff at Bird Rock, so it said 20 feet, may have been 30 feet. Okay, so if it had been 30 feet, well, if we look in the Nautical Almanac, what's the dip for 30 feet? Okay. So if I was wrong on my estimate for height of I, we used a height of I of 20 feet, and that would give a dip of minus 4.3.
Yeah, it'd be like 5.3 at 30 feet.
So at 30 feet, it would be 5.3.
Yeah.
All right, so the HO would have been 1 degree smaller, so it would have been 1 mile or so back this way. It would have been about there, right? So if that was accurate for dip, what was it? 1.3, 5.3?
5.3.
Okay, so that gets us within about a mile. Now we are back to August 11th. Okay, this is going to be the noon sight. And the first thing we're going to do is predict when that's going to happen. And we might do that early in the morning. So how do we do that? Well, we go to August 11th, and we look at the bottom of the page, and we find something called Meridian Passage. Everybody see that? 5 minutes, right? Does everyone agree with that? Meridian Passage?
Yeah.
Okay, what does that mean? That means the sun passed the Greenwich Meridian at 12 hours and 5 minutes GMT. That's way to the east of us. We're 117, and then we were about 15 some odd minutes, right? So for 117 degrees, 15 minutes. If the sun is moving at 1 degree every 4 minutes, so we didn't take the number of degrees to the west we think 117, and then 15 minutes is about 1/4 of a degree. So we multiply 117 times 4, add another minute, and that's how many minutes it's going to take for the sun to get from the Greenwich Meridian to us. So when we multiply 117 by 4, 117, let's see, 0.25, right, times 4, that gives us 469 minutes, doesn't it? 117.25 is 469 minutes, right?
117 times 4?
117.25 times 4.
Okay.
Where do we get that number? We're at longitude, our DR longitude is 117 degrees, 15 minutes. So 117.25 times 4 gives us 469 minutes. Okay, but we're dealing with hours and minutes here. So let's divide 469 by 60, and that turns into 7.81 hours. So 7 hours, and then we've got to turn 0.81 into a number of minutes now, so let's just subtract 7 from that. Now we got 0.81 times an hour, 60, and that's 49 minutes. So 7 hours and 49 minutes. Okay, everybody with me so far? Okay, so what we did was we found out where Meridian Passage was. We looked at our DR longitude, 117 degrees, 0.25 minutes. We know the sun's moving at 1 degree every 4 minutes, so we multiply that number, 117.25 times 4, we end up with 469 and 469 minutes, and that's the same as 7.81 hours. So 7 hours and then 0.81 times 60 gives us 49 minutes. So that gives us then 54 minutes. 12, 17 is 19 hours. 19 hours, 54 minutes, Greenwich Mean Time. Now, if we're actually just trying to set our alarm clock so we get up early to start shooting it, and we might want to convert back to the local time zone. So this time we subtract 7, that's 1 plus 7, and at 12 hours, 54 minutes, local mean time, that's when the sun should be passing our line of longitude. Now, let's talk a little bit about the mechanics of this. So what you're going to do is you're going to want to be up on deck, looking through your sextant, looking at the sun, getting it all lined up. And what will happen is the sun's going to go up higher and higher in the sky. It's going to hang there for just a few minutes, and then we'll start going down. But if you get up there right when it's going over, you might have done a calculation wrong, or you might have to fiddle with your sextant more, or it might be a cloud going over or something. You really need to get up there early. So I'm recommending that you get up there 10 minutes early. So if we subtract 10 minutes from this, we get up there, we start shooting at 12 hours, 44 minutes, according to our watch, set to local mean time. And then what we do is every minute that goes by, we write down what the HS is. And how do you do that? How do you time it? Well, someone could time you and say mark at each minute, or you can make a recording of yourself saying 10 minutes, 30 seconds, 20 seconds, 10 seconds mark, and so on. You could do it that way. You just look at your watch and then look through the seconds. There's a number of ways of doing it. Because the sun's going up and it's slowing down, it's hanging there for several minutes, you don't have to be all that precise about it. But you try and get a reading in about every minute. And they might be a little bit all over the place, go up and down and whatnot, but it should be a pattern of getting bigger and bigger and bigger, hanging around the same for a few minutes, and then starting down. And after you got 2 or 3 readings with it going down, you've pretty much caught noon, right? It's right one of those middle readings you had. Now, if one of them was way off, throw that out and use the ones that seem more, that are all more like each other. Okay? So let's say that we had, we were up there at 12:44, and it did turn out to be at 12:54 when we actually measured it, and we got an HS of 72 degrees, 0.8 minutes. And it was that way for several minutes. So let's say that when we were up there shooting, it was like it went up from 68, 69, 70, 71. It is going faster, really. What 70, 71.5, 71.7, and then it was 72 0 minutes, 72 0 minutes, 72 0 minutes. Then it was 71 degrees 58 minutes, 71 degrees 45 minutes, and so on. We've now tracked it going up and starting down. And so right at the top, the highest point in the sky it got was an HS of 72 degrees, 0.8 minutes. Okay? Now, let's say that, again, we're at 20 feet for that, just for the heck of it, like we used last time. So our dip is minus 4.4, because we still have to do the sextant thing. And that gives us, if we do the subtraction, oftentimes what I do here is I make it 71 degrees, 60.8 minutes. Okay, so if I do that, make this 71 degrees, 60.8, which is the same as 72, 0.8, minus 4.4, that gives 0.4, and 60 minus 4 is 56, 78 degrees, 56.4 minutes, now that I've corrected for dip. Now, just like before, we do a main correction, okay?
Well, you went way from 72 to 78.
Oops, 70, you're right, sorry about that. 71 degrees, late in the day. So it's 71 degrees, 56.4 minutes. All right, that sound better?
That's
Yeah.
Okay.
So that's where the sun is due south of us.
Yeah, after we've corrected for dip.
Okay.
But we still have to correct for the main correction, right? So what does that turn out to be if we go to the table in the almanac for the sun for April to September, you know, we're bracketing 71 degrees, 56.4. What's our main correction going to be? I hear someone saying a number back? 15.6? Okay. 15.6. That's 0.0. 7.5 is 12. 72. 71 degrees, 72.0, or 72 degrees, 12.0. And now we have an HO, don't we? 72 degrees, 12.0 is the HO. Okay, so we've now corrected the sextant. That's step 2 of what we've been doing all along. The next thing we would do is find the position of the sun, except we don't care about the GHA now because we're on that same line of longitude or just about. What we care about now is the declination. So the declination is north. It's 14 degrees something, isn't it? Because we just looked that up for the last site. What's our someone tell me our declination? North 14 degrees, and what were the odd minutes?
54.2.
54.2. And now we have a little d factor of minus 0.7, right? So we combine that 0.7 with 54 minutes, and what do we get? Can anyone tell me that from going back to the minute and seconds pages where it says V or D correction? Looking at the column for 54 minutes, what does a D of 0.7 give us? Oh, okay, so this is already corrected for D. That doesn't sound right, actually.
Yeah, that was 20.
Okay, so let's just cross this out and not give a corrected number, and let's say declination for the day and the hour is what? It's 14 degrees. What is it?
19, let's go 19 hours. North 14.
Okay, we're looking this up for 19 hours.
North 5th.
19 hours, okay, so at 19 hours on August 11th, what was the declination?
North 5th, 14. 56.6.
56.6. 56.6, okay? Little d of minus 0.7 combined with this 54 minutes gives us what? 0.7 with 54 is what? Isn't it about 0.6? Okay? I mean, it would seem to be that. So we end up with north 14 degrees, 56.0 minutes. That is the declination. Okay? Okay, everybody happy so far? We all got all similar numbers? All right, now, here is, I'm gonna write this down, but here's a formula I would like you guys to remember. And write this down and paste it or tape it into the lid of your sextant box. So hang on a second. I'm going to give you the formula for latitude, okay? There's 3 possibilities here to deal with. If latitude and declination are the same name and latitude is greater than declination, then latitude equals 90 degrees minus the HO plus the declination. Same name. Let me put same name.
When you say name,
North or south? Right. So they're each going to have a hemisphere to be in. So if we're in the same hemisphere as the sun, and it's at 14 degrees or so, and we're at 33 degrees or so,
We're north.
it's the same name. and our latitude is more than the declination, then this is the formula we use. Okay? Now, if it's summer, if the declination is north, that's always going to be the case, because if we're here in San Diego, we're not in the tropics, right? If we were in the tropics, it's possible that they could be the same name, but the declination is actually higher than our latitude. Like if we were at 5 degrees north latitude, and the sun's declination was 14, well, we'd be looking to the north when we did this measurement. And under those circumstances, if latitude and declination are the same name, okay, and the latitude is smaller than declination, then, let me make sure I got this right here, then latitude equals declination minus 90 degrees minus the HO. Okay, so we take the declination, we take this number. In each of these cases, you subtract the HO from 90 degrees. Let me make sure I got this right. Yeah, okay. So that's the second case where the latitude and declination are the same name. There's only one other possibility. If latitude and declination are contrary name, then, and it doesn't matter which is bigger or smaller in number, then latitude equals 90 degrees minus the HO minus declination.
So in all cases, it's 90 degrees minus HO.
You have to, in each of these, you subtract the HO from 90. Okay? So this is the sort of thing, it's, easy to forget if you go for a while without doing this. So if you just write these three little equations down, then you got it. Okay, so with that being the case, what did I just do with my other thing here? Oh, here we go. Okay, so let's go ahead and we are in this first instance here. Latitude and declination are the same name, and latitude is greater than declination. So this is our formula. Latitude is 90 degrees minus HO plus the declination. So if I apply that to here, latitude equals 90 degrees minus the HO plus declination. Then if we take the HO from 90 degrees, 89 degrees, 60 minutes. We subtract our HO from that because we just corrected the 72 degrees, 12 minutes. We end up with 89 degrees. Okay, that is 48 minutes, 17 degrees, 48 minutes. That's that corrected number. All right, plus the declination, which is 14 degrees, 56.0. Yeah, I will. Let me do this addition here, and we'll go over it. 8 and 6 is 14. Okay, 5 is 10. That's 104. That's 31 degrees, 104, or 32 degrees, 44 minutes equals latitude. So once again, let's look at it again. The ingredients to this are our HO and our declination. That's what we need for this formula. So we take the HO and we subtract it from 90 degrees. Now, what I always do is carry over before the subtraction. So I take the 90 degrees, I turn it into 89 degrees, 60 minutes. It's the same thing. And from that, I subtract our HO, right, of 72 degrees, 12 minutes. I end up with 17 degrees, 48 minutes. Everyone see how we did that?
Yeah.
Okay. Oh, raise the page up. There we go. Okay, so we subtracted our HO from 90, and we ended up with 17 degrees 48 minutes, and then the declination was 14 degrees 56 minutes. So we added it, okay, and what we ended up with was 31 degrees 104 minutes, which is the same as 32 degrees 44 minutes, which is our latitude. Okay, and that's, again, I didn't actually take a noon side, I just fiddled it out to make sure it came out close to where I was saying our latitude was. So that mathematically is a lot easier to do than what we've been doing. In actual practice, it's complicated only by the fact that you've got to be up there, on your boat 10 minutes ahead of time. So you got to predict when it's going to happen. You got to be up there ahead of time, and you got to catch it, right? As the sun comes up, stays for a while, and then starts down, and you use that series of HS's staying the same to pick one, and from that to get your latitude. Okay. So it's a little bit more. The time sights we've been doing, if you can see the sun, you can see the horizon. The sun's more than 10 degrees off the horizon, you can get a line of position. With this, you've got to be up there right during that brief period when the sun has come up and it hangs there. Okay, now I'm going to go ahead and preempt the conclusion everybody comes to. It's pretty normal to say, okay, well, wait a minute, wait. If I'm up there and I am able to take this chain of sites and say there's 5 sites where the sun is at, where my HS is at, I don't know, what did I say it was, 72 degrees, and 72, 70, 72, I had 5 numbers that were there, and all I need to do is take that middle number and see what time it is, and then go in the reverse of what I did with the prediction, right, and see how many minutes I am from Greenwich, and I know my longitude, right? So now I got my latitude and my longitude. Wow, 500 years and nobody ever thought of that. Right? In fact, yeah, people have thought of it, but it doesn't work. Because what happens, it doesn't work very well, let's put it that way. Because remember, the sun goes up, and it goes up, and it does this kind of a pattern, and it hangs there for quite some time. And you may not be getting exactly the midpoint, and again, it's hanging there for 4 minutes, 5 minutes. If the sun's moving 1 degree every 4 minutes, you might be half a degree off or more off. So this is just too large a space of longitude over which to try and judge it practically. There is, however, kind of a method for doing that called equal altitudes of the sun. And that is, in the morning and on the way up, you catch it on the rising slope, and let's say at that point it's, 55 degrees, HS, and then you set your sextant up so exactly the sun touches the horizon at 55 degrees on the way down, and you split the time between those two, because at this point the sun's moving faster, and that's a lot more precise. So but again, it complicates a little bit if you've moved in the meantime. Like if 2 or 3 hours have passed, you've got to factor in the amount you might have moved to the east or west when you do that. But if you catch it, then you can kind of get your longitude that way. Okay? But if you got to be up there and shooting for the noon sight to get the sun on its way up and hanging there, this guy has to be really precise. I mean, it's got to kiss the sun right there, right then. You got to nail it right on the second. Okay, that's the only disadvantage to that method. It's in many respects, it's a lot more trouble than just taking a couple of time sites. Okay, so with the noon sight, it's mathematically less complex, but it's, from a practical standpoint, it's a little bit more demanding of the actual schedule you're on. I mean, you get ready for the noon sight, and suddenly you have a nice big mahi-mahi on the line you're towing astern. Suddenly you forget about the noon sight, you're going to get dinner in, right? And now the noon sight's all gone to hell. So there's a lot of things that could interrupt your ability to take that sight. Whereas the time sights, 5 minutes, take another one 5 minutes later, and you're fine. Okay? Predict a noon sight and try and get one of those just to see how that works. Now, if any of you are scheduled to go out on the Californian sailing this weekend, so if you're going to go out on that, that'd be a good way to do it. The other places, you obviously have to have a nice clear horizon to the south. So Coronado, you kind of have one there. You have one at Cabrillo National Monument. If you take the trail down to the, actually you probably would have it, there's a trail that goes down to the bay side that might be the closest thing to go for a noon sight. It doesn't go to the tide pools. It goes down to the bay, and it sticks out enough that you might get a clear horizon that way. And then Bird Rock, I think you can see directly to the south a little bit. So that would be a good place to go also and try and get one. All right?
You mentioned Coronado?
Coronado, yes. Yeah. Yeah, that would be a good one too. So just the beach, because that curves, you know, it curves. You got a good clear shot to the south. Okay. All right. Okay. So where we left it last time was all these various means of determining longitude, none of which were working by the time you get to the 17th century. So, but back to this guy, Galileo. Galileo was interested in solving this problem, and he thought, when he got his hands on the first telescope, that he might have a crack at it with the Jovian moons. But the problem ultimately ended up being that you need at least magnification of 30 and actually really 50 to be able to time it. He calculated that there'd be about 1,000 opportunities a year to be able to observe the eclipses of Jupiter's moons if you could see them and observe it. But the problem is, of course, you're on the moving deck of a ship, 30 to 50 magnification, that's a lot to ask for. So that, it just never worked out well. However, that did not stop Galileo from suggesting that a prize be awarded for somebody who could find the problem, the longitude, or who could solve it. So he was able to convince the Duke of Tuscany to put up a considerable amount of money for anybody that could solve the problem. Because of course Galileo himself thought, hey, I can solve this. It just takes a little bit of work and I'll do it and I'll be due for the money. Galileo was a military engineer, a mercenary engineer, and that's how he made his money, was often by the awards of prizes and things. And there were, by this time, in the early 1600s, there were several nations that had awards for solving the longitude problem. Most of them were Mediterranean nations. Spain had one. There were other Italian states that had awards as well. Galileo, by the way, was also working in a lot of other fields. He was resident for a while at the Arsenal of Venice, during which time he wrote what is the founding document for modern science, called Discourse on Two New Sciences, in 1638. And he wandered around the Arsenal, and he looked at what he saw, the people that were doing problem solving by lifting heavy weights, moving things around, and he decided to turn that into a bunch of mathematical equations, and essentially founded the discipline of engineering. So this was the first work of engineering ever written, and the sciences were statics and dynamics, the engineering and the calculations for non-moving and for moving objects. And some historians of science regard that as the founding document of the scientific revolution. Didn't have much to do with longitude, but it did have a lot to do with systematizing the methodology of problem solving, which is what they were doing at the Arsenal of Venice, because it was the most advanced military, industrial, and social complex of its day, by far, more so than any other of the similar institutions that it was contemporary with at the time. So anyway, so with that established, prizes, prize for longitude, and a systemization of observation that translated what had formerly been an empirical way of doing things into a systematic and analytical way of doing things using numbers. Galileo really had a lot to do with that. And it went forward beyond him into other places. So for instance, Charles II was a navalist. His father, Charles I, had been executed. One of the reasons was for spending too much money on the Navy, with the ship money fleet taxing people. So they cut his head off, Parliament did, at the end of the English Civil War. When the Stuarts were restored, Charles II and his brother James II were totally into yachting and sailing, and just they loved the Royal Navy. And Charles wanted to build it up and also see it used as a manner of projecting power. So he was interested in any sort of scheme or device that might improve the potency of the Royal Navy he was working hard to build. The thing he liked, the only thing Charles liked more than the Navy probably, were really nice looking women. And so this one here, Louise de Querelle, if you've seen this picture before, it's in the Getty actually. It was one of Charles's mistresses. Her nickname was Fubs, which is impressive quality that she had. And Charles tended to name all of his royal yachts after her. They had official names. They were, however, always called the Fubs 1, 2, 3, and so forth. Anyway, a friend of hers from Brittany, Sir de Saint-Pierre, managed to convince her if she could get the attention of the king, he had an idea for solving the longitude problem by using by astronomy, by a lunar distance method, which of course had been proposed many years before by astronomers such as Johann Wegener, Regimentanus, and others. However, she convinced Charles that, we do need to solve the longitude problem. And it was deemed to be a serious problem because there was an increasing incidence of accidents or near accidents taking place as the Stuart Navy was being used as an instrument of national policy. So in 1673, Sir John Narborough, a famous admiral of his day, almost wrecked his entire fleet at the southwesternmost bits of land off of England, the Scilly Isles. It's a notorious area for rip currents and tides, weather that prevents observations, and lots of fog and things like that. At least that was the reputation it had then. Today, it's apparently a place where they raise a lot of flowers and things, and it's a vacation spot. So, but in those days, it had a dangerous reputation, and Narborough almost destroyed his own fleet as he was trying to navigate through there in a fairly thick weather. He had as an apprentice a young sailor named Clodesley Shovel. Narborough was a protege of Narborough, and so Shovel was duly impressed by the fact they had almost gotten themselves killed by running on these dangerous rocks in these islands. It was a notorious episode, and the diarist Samuel Pepys, who became famous for writing about anyone and everyone he associated with, including Charles and his brother James and all the people at court and all the naval figures. Samuel Pepys was the primary administrator of the Navy. He was the secretary of the Navy Board, and he also added his voice to the growing impetus to make navigation a foremost objective of national policy, of solving these technical problems. Now, Samuel Pepys suggested that we don't really have decent charts. What we really need is the equivalent of what we call today a hydrographic office. It was what the Spanish had called the Casa de Contratación and the Portuguese the Casa de India. So actually Samuel Pepys was instrumental in founding some of the institutions that ultimately served that purpose as the hydrographic office. Chatham House was one of those, and there were others, and they produced charts. And he also managed to have a permanent full-time position of Royal Hydrographer, and that position fell to the first hydrographer in history, Captain Grenville Collins, who produced this chart of the Scilly Isles, one of the first charts he produced, and total rational depiction of the space. Okay, so you have by the latter part of the 17th century an institutional response to these navigational problems, which is probably a step beyond what the Portuguese and the Spanish had entertained, and it had become an element of statehood. Well, Charles II's girlfriend convinced them that that wasn't enough. They really need to do more. They need a permanent institution devoted to solving the longitude problem. And so the very first big science project in history turned out to be the Royal Observatory in Greenwich. That was established in 1675. The design for the building was produced by Sir Christopher Wren, who also designed St. Paul's Cathedral and a number of other prominent buildings in London. And if you notice, there's this tower sticking up, that's the actual observatory. He drew inspiration from the Tower of the Winds in Athens, which is a 1st century BC observatory. And noteworthy about the Tower of the Winds, even though it was the Tower of the Winds, when they built it, they used the 8-point mariner's compass, not the 12-point compass on which the winds and direction of the winds are based. So back in ancient Greece even, they were using the 12-point compass. This was a period with the proliferation and the invention of scientific instruments, including very accurate instruments for measuring altitudes of bodies, and also clocks as well. And beginning to employ clocks in a systematic way as instruments of astronomy. And they also established, with the establishment of the observatory, the first full-time scientist in residence of any European nation. This was John Flamsteed, who became the first astronomer royal. John Flamsteed also got to say exactly where the prime meridian was. At that time, every country had its own prime meridian, but England's prime meridian went through Greenwich, and ultimately, that's where it goes through. And interesting enough, every astronomer royal gets to decide for himself where that line goes. So that line is moved by inches back and forth every time there's a new astronomer royal. So there have been lots of prime meridians, right? It's just one of the prerogatives of the job. Anyway, Flamsteed was given the job, but he was told, okay, you get a salary. It wasn't much, but you have to buy all your own instruments, so you have to make them. So he did, and he bought his own instruments, and he began to put into practice observing, first of all, picking up where Galileo had left off, and observing the Jovian eclipses. And then turned his attention to the lunar distance method and to the moon. Here's a modern picture of the Greenwich Meridian, where the last astronomer royal had it, and then the inside of the observatory at Greenwich. And you can go there today. It's open to the public. It's a great place to visit. Well, the British weren't the only ones doing this. The French were also hard at work doing it, and they put their own scientist in residence at their national observatory, which was founded in 1672, and it was inhabited by Giovanni Cassini. Cassini, and there have been famous satellites named after him, and there are places on the moon, craters named Cassini, and so forth. Very famous name. It was a generation of 5 fathers and sons who were astronomers over the course of more than a century. All of them, the head astronomer at the Royal Observatory in Paris. And they were also devoted to several things. This was during the age of Louis XIV, and he wanted an accurate method to determine longitude, not so much because of navigation, but because he just wanted France to be as big as possible, and he had it into his head, the way it's shown on maps isn't as big as it really is. So Giovanni Cassini used clocks, and he used eclipses, and he used the Jovian method to determine longitude. Broke the news to Louis XIV, which took a lot of nerve to do. Sorry, sir, France is actually smaller than you thought it was, which made him quite unpopular with Louis XIV, the Sun King, for a while. Said, you have cost me more of my territory than the Spanish and the English combined, he said. So he wasn't really popular. It's not good to speak truth to power, I guess, then or now, and but he kept his job anyway, and they continued to work on the longitude problem in a race, almost like the race to the moon, between the main powers of the Cold War. A scientific objective, but it is also a matter of national pride. Now, the French were also very keen on producing the world's best clocks, so that a clock might be able to solve the problem. And they managed to lure the foremost horologist and scientist from the Netherlands, Christian Huygens, from Amsterdam to Paris to get to work on one of these clocks. Now, there have been clocks around in Europe for a long time. The pictures you see to the right are the clock in the Salisbury Cathedral that dates to the late 13th century. And they tended to have weights that would swing around and so forth. Huygens' notion was to use the pendulum as a way of regulating the motion of a clock. What you had to do is you had to have a way of storing energy by either by gravity or by storing it with a spring or something. You had to have a mechanism that released the energy. You had to have a mechanism that regulated that release of energy, so it was always coming out at the same rate, regardless of whether the spring was tight or slack, or whether the weights were up or down. And even if it was a spring, when you were winding it, that release had to be the same. So Huygens managed to solve all those problems, but he solved another one as well, which is interesting. You'll notice in that picture, to the upper right, showing his pendulum, and as the pendulum swings, the pendulum doesn't just swing back and forth. At each extreme of its swing, it rubs up against one of these two sort of curving plates, right? Those are called cycloidal cheeks. As it turns out, if you let a pendulum just swing as a pendulum, it doesn't regulate time very well. Even if that swing is regulated by a sophisticated mechanism, because a perfect arc, because the Earth's motion it stays the same. But for some reason, if a pendulum makes the motion of a cycloid, that is, it runs along an arc and then pitches up at one end, runs along the arc, pitches up another, it will be a perfectly regulated timing mechanism. And what those cheeks are there to do, it's to turn the movement of the pendulum into a cycloid. A cycloid is also described as the point on a circle, the point on a wheel as it's moving along a horizontal surface. It's the arc that point makes. And so Huygens discovered that as well. If you look at a grandfather clock today, you can see those same cycloidal cheeks on them. Harrison clocks 1 through 3, even though they aren't pendulum clocks, they're balance beam clocks, they still use this principle of cycloid to regulate their mechanism. If you go to Greenwich and you see them running. Or if, I don't know if they still have it, does the Natural History Museum still have its Foucault pendulum? The thing that swings back and forth. Okay, so look up, I haven't seen it for years and years, but look up and you should see the cycloidal cheeks that the wire makes as it goes back and forth. It runs up against them, and even though it moves very slowly and so forth, that pendulum is not describing a true circle, it's describing a cycloid, okay? It turns out also that cycloid helps with pendulums because the rate of a pendulum can change depending on latitude, and they determined that by experimentation at the end of the 18th century. Okay, so there were problems with pendulum clocks. One of the problems, of course, is that you take a pendulum and you put it on a ship, and the ship's moving around. That's not so good. The same problem you have with an astrolabe or a mariner's quadrant. Everything is moving around. Nonetheless, they tried to do that. So Huygens developed a clock that he thought would work if you took it to sea, and there was actually a guy that did it. His name was Major Robert Holmes, or Sir Robert Holmes of the British Army, who was also a sea captain. And he took it to sea from Bristol, I think, to Portugal, and he couldn't get to work properly. And then, following that, he was friends with Huygens. You kind of wonder how a French scientist, a Dutch turned into French scientist, was given a possible weapon to an English soldier, but nonetheless, that's what happened. And Holmes in 1663 decided he was sent on an expedition to raid the Dutch in the Mediterranean. This was at the outbreak, I think, of the Second Anglo-Dutch War. And he wanted to know precisely where he was when he could, so he took one of Huygens' clocks with him, and they had better luck with that. Okay, but not perfect. He could actually get to within about half a degree to 3/4 degree of longitude on a regular basis using one of Huygens' clocks. That itself was a major improvement over anything anybody else had done. Well, another guy who thought he might solve the problem was the scientist Robert Hooke. Robert Hooke was a contemporary of Isaac Newton and Robert Boyle. He was one of these scientific entrepreneurs. He was a prominent member of the Royal Society. In fact, he was the curator of experiments at the Royal Society. And Newton just detested him, just hated him. But Boyle was a good friend of his and kind of his protector. Robert Hooke made all sorts of inventions, including the microscope. And his most famous work that he published is called Micrographia, and he produced all these really beautiful images of all of these animals so tiny no one had ever seen them. He unveiled an entire microscopic world that people were up until then totally unaware of. Ultimately, that led to theories of disease and so forth. What's really interesting about Robert Hooke, there are several of the microscopes that he built. This is a picture of one of them, and they all have similar characteristics. Some of the images, the highly detailed images in Micrographia, could not possibly have been seen by any Hooke telescope that we have, right? He was using something that had a far higher magnification than anything that has survived to the present day or that he wrote about. So he's a secretive guy. He tended to take patents on these things, and on this one he was working on when he died, he never actually took the patent, and no one has ever found the microscope that Hooke used to create some of the drawings that are in Micrographia. It remains today one of these great mysteries. Anyway, Hooke also claimed to have solved the mystery of creating a perfect clock that could so closely mimic the movement of the Earth and the planets that it could be used to find longitude. Now, Hooke developed a lot of devices or elements of those kinds of machines. Ultimately, many of those inventions ended up going into a sort of an overarching machine called the dividing engine that was invented by a guy named Jesse Ramsden, but he was using a lot of Hooke's inventions. There were about 8 of them at one point in London, being used to create quadrants. They were called octants by that time, and sextants and things like that. So you have a machine that makes other machines. And to some degree, this thing was programmed like an analog computer, and in some respects also resembled the Antikythera machine. So Hooke had a lot to do with that. Hooke also invented other things such as the bimetallic strip and the universal joint that went into some of his mechanisms. Interestingly, John Harrison, the horologist who's credited with the invention of the chronometer, is almost always given credit for inventing those things, but in fact it wasn't him, it was Robert Hooke that invented them. He also invented other things that Harrison was given credit for, such as the anchor escapement, and that is the device that allows the release of energy in a regular way, a regulated way, an even way, no matter how tight the spring or if it's being wound, and also invented very sophisticated balance springs to power his device so that his device would not be reliant upon gravity with a pendulum the same way that Huygens was. And Hooke was one of these secretive guys. He actually made a huge amount of money after the Great London Fire in 1666 because he was also a surveyor, and he made tons of money with people that wanted him to survey their property after all the buildings had burned down. And if you hired Hooke to do your property, you paid him well enough, magically your property got bigger at the expense of your neighbors because nobody could tell what the boundary lines were anymore. So Hooke made a killing on that, and after he died, they found tens of thousands of pounds in cash in the chest under his bed. Anyway, an interesting character for whatever the case. He also was a contributor to 2 of the greatest horologists of the day, Thomas Tompion and George Graham. Now, Thomas Tompion used pendulum clocks, and Hooke contributed to that. And today, if you go into the Greenwich Observatory, there are 2 really big Tompion pendulum clocks that still run after all these years in the observatory itself. George Graham was another clockmaker, a horologist, who was making really fantastically detailed and accurate clocks and using Hooke's invention of the balance spring to power them. Hooke was also instrumental in creating these devices that were automated replicas or models of the solar system called ORIs. We've got an ORI-like thing down below in the exhibit Art of Navigation. For a long time, when people wanted to indicate in their portraits that they were sophisticated intellectuals and that they were subscribers to science, you would have an object in the portrait. They weren't called ORIs, they were called, the name will come to me. Anyway, those ended up getting replaced by ORIs, which are mechanized versions of it. If you go on eBay, you can buy an ORI if you want and have it in your own portrait if you like. But anyway, those intended to use the kinds of mechanisms that Hooke was inventing. And again, Hooke never saw the Antikythera machine or anything like it, but it turns out when they brought it up, there are a lot of things about it that resemble the devices that Hooke was working on as well. Okay, well, the impetus for doing this was obviously for navigation and empire building and making navigation a lot safer and more regular. That all became much more urgent when Sir Cloudesley Shovel in 1707, remember, he was the protege of Narborough and almost lost his life in the Scilly Islands. He was coming back, he was an admiral in 1707, he was coming back after a highly successful campaign against the French in the Mediterranean. Sailed through the Mediterranean, sailed through Gibraltar, and was approaching England and trying to go up the English Channel, and they had several days without any starlight, any stars, or without any sun, and they were going by dead reckoning. And unlike his earlier episode in the Scilly Isles, actually Cloudesley Shovel in his flagship, the 80-gun HMS Association, ran on to a rock called the Clerk and Bishop Ledge, and the association broke up. And there were about 4 or 5 other vessels that broke up along with the fleet. And there was only one survivor from 2 or 3 of them, but from the HMS Association, there were no survivors. Okay, everybody on board died. There was this story that Shovel had washed ashore he was kind of an obese guy, and he might have floated better. And he was smothered in the sand by the people on the islands who wanted his clothes and his jewelry and so forth. That is probably not true. There was this other rumor, however, that has persisted to this day, that just a few hours prior to the accident, an ordinary seaman approached him on his quarterdeck and said, "Admiral, I've been looking at my chart and everything and taking observations, and I think we're sailing into danger. I think we're about to hit these islands here." Shovel was outraged that an ordinary seaman would attempt to correct his navigation and had him hung instantly, or so the story goes. And that got repeated in Davos Sobel's book about longitude. But if you think about it, you can't just execute a guy on the spot, even if you're an admiral, right? It requires a court-martial and a bunch of formalities. The ordinary seamen, they just didn't have charts and backstaffs and things to carry around, and if they had been, they were going, "What are you doing?" They just didn't have access to that kind of stuff. And the third thing is, there were no survivors from the association. What, they didn't have a radio? How could anybody find out about this story? But nonetheless, these stories persist. So in any case, it was a horrendous accident, and it occurred about the same time that all of these people were trying to promote the idea that a longitude solution is possible. And you know what? This horrible accident might have been prevented if only people had been able to find their longitude. It's not clear that that's the case, because all of these schemes, except for magnetism, you need to be able to see the sky, which they hadn't been able to do for 3 or 4 days. It also turns out that at this time, until Halley got involved with things, just right after this, people didn't realize that magnetic variation changed over time. They knew it changed over geography, but they didn't know it changed over time. So if you look at a modern chart like your San Diego Santa Rosa Island, it'll tell you what the magnetic variation is, and it will say in the compass rose the annual increase or decrease, okay? Well, nobody had taken note of that for almost a century when Shovel was trying to sail up the English Channel, and it turns out they were way off in their compasses in understanding what the variation was. And the third thing was the whole area is beset by strong currents and tides and things that could have just taken them out. So it's unlikely that any longitude solution then available, or what would be available for a long time, would have solved the problem. At least not by astronomy, it wouldn't, or by clocks, it would not have. Nonetheless, people thought that it might and promoted this as a horrible catastrophe that might have been prevented. In its day, it was as famous as the Titanic is now, okay? Possibly because it was promoted in public perception to being both a disaster and possibly a preventable one. So what were some of these ideas that people were coming up with? And they were all interested in basically, if they could first promote the idea of a prize. They needed a lot of money. The government put up a lot of money. Surely they could find a solution. And that is how much of science got funded, was by prize money. Finding the solution to a problem, someone gives you a prize. That was against Galileo's approach to the Duke of Tuscany and so forth. So one of the longitude projectors came up with the idea, Sir Kenelm Digby, based upon the medical system promoted by a guy named Paracelsus in the early 16th century. Paracelsus was the founder of homeopathy. And there are several principles that homeopaths believe in. One of them is that if you've got a medicine that works, if you keep giving the patient smaller and smaller doses of it, the medicine, it gets more and more powerful the more diluted it gets. But the other thing is that there is some sort of insensible connection that links us all, and that all the objects and all the people and all the beings in the world, so that you could actually treat a wound by treating the weapon that caused it, or the thing that caused it. So if you accidentally cut yourself with a knife, right? If you treat the knife, then your injury will get better, right? That was a premise of simultaneously, through means unknown, but that supposedly happened. Well, Kenelm Digby thought, well, he worked on, just like people were alchemists and stuff, he worked on a substance called the powder of sympathy, which he believed elevated this, and it was one of the key elements of homeopathy. And it's that you have action at a distance. That is, there's no explanation for why things can happen instantaneously while they are separate, but they can happen concurrently without a known connection. This was, however, a hypothesis of a connection. So The idea came forth that, well, if you could have this connection and you could regulate it, then and it worked even at the greatest possible distance, then maybe you got the solution to time. And he never got any further with that, but then in the later 1600s, a proposal came out, a longitude scheme that said, well, if you injure a dog and you keep the dog in, say, on the ship, and then you bandage the dog, and then you take the bandage from the dog and dip it in hot water, the dog will feel the pain and yelp, right? So if the bandage is kept at the Greenwich Observatory and the dog goes on the ship, then all you got to do is observe the dog at precise times, an agreeable preconceived time, and when the dog yelps, you know what time it is, then you can determine your longitude. I mean, it was a totally ridiculous notion. Nonetheless, some people, including Thomas Sobel, took it seriously. Apparently, it was a product of Jonathan Swift's Scribblers Club, because Jonathan Swift was parodying and satirizing all of these weird longitude schemes that were coming out. He just thought, and his friends thought, Swift and Addison thought it was that the whole thing was just utterly ridiculous, and these were all crackpots that were coming up with these get-rich-quick schemes, and the powder of sympathy was one of those. Finally, there was another guy named William Whiston, who was a minister and a navigation teacher, and Whiston said, I have this method for determining longitude that is not based on astronomy, and it's not based on magnetism, and it doesn't require really a clock. And all we need is a really big prize, and I'll tell you what it is. I'll tell you myself, so I can win the prize. Well, somehow he managed to get people convinced to do that, and he got Isaac Newton to agree to speak in favor of it at a meeting of the Royal Society and draft a letter to King Charles II to say, you know, in addition to the observatory, we ought to be putting up a prize to just unleash all the creativity from all these people. And what Newton was after really was he was a bit, I guess, disappointed at the slow pace of the advancement of science, and he thought it could be jump-started if these prize systems were established. And so he was in favor of this. And so in 1714, Queen Anne, 12 days before she died, she didn't do it, but Parliament passed an act that she proposed. It wasn't Charles II, it was Queen Anne, his daughter. It was James's daughter, I think, excuse me, James II. Anyway, the deal was, this came out in 1714, and it put up a prize that anybody who solves a longitude problem gets 20,000 pounds, which was a vast sum in those days. Now, Isaac Newton put his idea in, and he said, okay, yeah, that's okay, but it can't be a thing where you are measuring the longitude. You have to find the longitude. You can't just record it. So in other words, a clock which kept going by a regular rate would be ineligible for the prize because it was only keeping the longitude, not finding it. You have to be able to find it no matter what. So astronomy would work if you could do that. Magnetism would work if you could figure out a way to do that. But clocks, no, because there wasn't really a good way to determine if a clock was accurate or not without some outside reference, which gets you back to astronomy again. So the way that Longitude Act was written, it did two things. It established the amount of money, which is 20,000 pounds, with less money that is if you could find it within a fourth of a degree, less money if it's with a half degree, less money yet if it's with a degree, and then that's it. So establish the amount of money. They established a criteria. What would be considered an adequate longitude solution? You know, that was the other criteria. And the other thing that it did was it established a group of people who would listen to all these proposals and come to the conclusion of whether they had any validity or not, and award the money if the solution was put forth. And so it was the first modern board of any kind, called the Longitude Board. Kind of interesting. I work for a board now, so many of us do. But this was the first time ever that there was ever any board, was the Longitude Board. And so it had sea captains. Isaac Newton was on the Longitude Board. It had Grenville Collins was on it. and these people would evaluate the proposals, of which there were a slew of them. And Swift wasn't the only one making fun of things. The political cartoonist and satirist Hogarth, in his book called The Rake's Progress, showed the progress from some well-to-do young guy as he, through decrepitude, sank down and just made a mess of his life. But one of the waypoints along the way of this young wealthy guy becoming a complete derelict was when he became a longitude schemer. And so this is an image taken from the insane asylum in London, which was called Bedlam. If you've ever heard the phrase Bedlam, it was actually a place called that, under Bedlam, right? That was actually the insane asylum. And amongst all the crazy people here, prominent is somebody pursuing a longitude scheme in the background, drawing up arcs and tangents and things of that nature. The implication being all these longitude schemers were just crazy, you know. So anyway, the longitude was established the 12th of Anne in 1714. And after that, and the money was put up, William Whiston said, okay, here's my plan. Give me my money. And his plan was to take several hundred ships and moor them all over the ocean. And it was believed if you dropped a sea anchor deep enough into like 600 fathoms, the ships wouldn't move. The water down there doesn't move. So they would hold their position. And periodically, they would fire rockets into the air. They would explode, and each one would have its own characteristic explosion, and anybody at a distance would be able to measure from that angle and the bearing, find that ship, and be able to determine where they were. Now, it sounds completely absurd, but in a way, it's a little bit like that thing with assumed latitude and assumed longitude. You start out with a known position. It's a light ship, right, but these were spread across the middle of the ocean. There were hundreds of them proposed. So several things wrong with it. There weren't hundreds of ships to put out there. B, the ocean is way deeper than Whiston thought it was, and there are underwater currents that move around, so there's no way to hold them fixed in space. The ships themselves would have to have a fairly decent timing mechanism to fire the rockets at the right time in the right place. And then you've got to be sailing around close enough to one, even though there are hundreds of them, you can see it go off and measure the angle and the distance. So as weird as it was, there are some aspects which is not dissimilar to geostationary GPS satellites. Okay, or they're not geostationary, they move around, but a system of satellites that use a geostationary system. And in a way, the plotting part of it is not that much different in some respects than what we do with that assumed latitude and longitude. So crazy guy, but some of his things actually ultimately kind of came into being. Unfortunately though for him, everybody thought his plan was just so unbelievably stupid. He was like, go away. They didn't want anything to do with William Whiston, and that was kind of the end of that. However, the Longitude Act continued, and there was some kind of discrepancy as to whether, okay, if the Astronomer Royal solves the problem, he's a paid government employee, he's paid to solve problems like this, is the Astronomer Royal eligible for this big, huge sum of money? And so Flamsteed got to work, and he thought, again, I think those Jovian moons, that's the way to go. And of course, it didn't turn out to be the way to go any more for him than it did for Galileo, but that was the first thing he turned himself to before he turned all of his efforts to trying to solve things through the lunar distance method. Now, inserted into all this stuff, there's another little subplot, and that is the idea of making observations to determine the nature of the universe. So Johannes Kepler revised a set of mathematical tables called the Rhodolphin tables and predicted in 1731 that the planet Venus would cross the sun, face the sun. And if you could observe that from different parts of the Earth, you might be able to determine the proportions of the solar system and ultimately the size of the solar system and even the universe. He just predicted that would happen. An English astronomer named Jeremiah Horrocks actually did it and observed the first transit of Venus in 1739, creating a device that kept him from looking directly at the sun. But it was just one observation, so he couldn't do it, but he proved it could happen. And Edmund Halley then proposed that, the next time these things happen at an interval of 105.5 years, there's a pair of them 8 years apart, and then following that at 120.5 years, there's another pair of them 8 years apart. So the next opportunity is going to happen in 1761 and 1769. Halley wasn't going to be alive then, but he said, if all the nations of the earth could get together to make this observation, we would all come together on something that was would be for the good of science, for understanding nature, and it would bring all the nations of the world together on this one project we could all contribute to, and that would be send a bunch of scientists to different parts of the Earth to simultaneously observe the transit of Venus, and you'd be observing the same thing take place from widely distant points on the Earth, and thereby through parallax, be able to determine the distance between the Earth and Venus and the Sun, and then and the other things out there. So that was proposed by Halley several years after Horrocks did his observation. And so a lot of what was going on with astronomy wasn't just longitude, it was actually trying to solve larger problems and addressing larger, bigger issues. But it was perpetuating the concept of big science and institutional science as supported by nation states, becoming an element of statehood. And of course, Newton was a foremost proponent of that. Newton believed that the only way they were going to solve the problem was through astronomy, and that would be through the lunar distance method. Now, the problem with that is that you're using the sun as the indicating mechanism, like the hands of a clock in a way, and it's moving across a background of stars that by comparison are infinitely far away. I mean the moon, if I said the sun, I meant the moon. But there's problems with that too, because the moon's motion isn't all that predictable. It's influenced by not only the Earth's gravity, and Newton kind of invented gravity too, but the Earth's gravity, or invented a concept of gravity we use, and the sun's gravity. It's what's called what they call the three-body problem. It made for a really complicated pattern for the moon to go through. And that is what actually Isaac Newton devoted a goodly part of his life to, was trying to solve the problem. He said trying to solve the problem of the moon was the only intellectual exercise that ever gave him a headache, right? And he just worked on it incessantly. So he was creating the theory that would solve the problem that was supposed to be being validated by John Flamsteed, okay, through observation. And so the two were supposed to work together. What Newton was doing and Flamsteed was doing, and Newton's pal Halley was helping out with the observations. Flamsteed, however, then they were waiting for him to publish his book on observations of the stars and the moon, a giant catalog of stars. Newton got a hold of Flamsteed's book and then decided to publish it for the benefit of other astronomers. And Flamsteed says, whoa, wait a minute, that's my book, you can't do that. I took all those observations with my own instruments I paid for. That information belongs to me. And Newton and Halley said, well, you've been paid by the British government for all these years to do this, so sorry, we don't think so. It belongs to the state. It doesn't belong to you. You're a government employee, And so I think Newton and Halley printed 100 copies of Flamsteed's book and distributed it. Flamsteed went out and bought every single one of them and burned them all. He was so ticked off at all of this. In any case, they kept working on it, and Newton never did solve the problem. Ultimately, it did get solved, actually, by a series of mathematicians. Laplace contributed heavily to it, building on Newton's theory and developing Newton's efforts to solve it kind of relied upon complex forms of geometry, but also early proto-versions of calculus, which Laplace then took further, and that was taken further yet by Leonard Euler and Tobias Mayer. And collectively, those three guys developed a set of tables that finally was able to define the motion of the moon against the background stars. That was compiled into a document, the first Nautical Almanac, from which the ones you're using is a direct descendant, and that was essentially overseeing its publication by the fifth Astronomer Royal, Neville Maskelyne, and published in 1763. Okay, the first copy of that was given to Captain Wallis, that sailed in an effort across the Pacific to determine if Terra Australis Incognita was really there or not. And he happened to discover the island of Tahiti and was able to define its latitude and longitude, the first time ever that had been done using Maskelyne's tables from his Nautical Almanac of 1763. It was a complicated process to reduce the site. You had to clear the observation from all of these things, like in addition to, like we do with semi-diameter and dip and refraction, there were a whole bunch of other factors affecting the moon that you had to use. So it was pretty complicated. It was fairly inaccessible, at least in the form that Maskelyne first produced it. So you have you're right now on the cusp of an intersection of two things. One of them is the search for longitude. Three things, actually. The search for longitude. The second is a mission for which longitude would be important and contribute to. Now they had this one spot in the middle of the Pacific that seemed an ideal place, along with others, to observe the transit of Venus. You had to be able to navigate there accurately and find your position to be able to do that. So now you have a goal or an objective for that mission. And the third thing was the other regulating mechanism that affected all human beings, and that is what happens when you get out of sight of land and you stop. Your access to fresh food stops, and your body becomes a clock, and you start to lose not be able to synthesize collagen from vitamin C, and that horrific consequence, the third of those three things, will be the subject for next week. All right, that's it. Thank you.